anyways, let's get started. Okay, so last time we finished up metric spaces, which was a nice little side chapter. Now we're coming back to topological properties. And so for chapter 6, the topological properties that we're going to be interested in are have to do with how connected a topological set is. How can I make this make intuitive sense? We'll go into the definition and see a discrete example right out the door. So maybe, I don't know. Topology is always so abstract, it's hard to come up with a good intuition to put in your head without just going through it. So maybe we'll just jump right in on this one. So connectedness, that's what this whole chapter is about, and that's what the first section is about. We're going to take a first look at some connectedness properties. So let's start. So let X be any topological space. Then we're going to define three things. X is disconnected, it is not connected, if I can find two open sets, U and V, that have no intersection and whose union, two non-empty sets, U and V, that have no elements in common, but when you union them together, you get all of X. So it's like X is disconnected if I can divide X into two open sets. If I can take X and split it into two open sets, then X is not connected. It's disconnected. That make sense? And then X is connected if it's not disconnected. So every set is either connected or disconnected. If it's not connected, it's disconnected. If it's not disconnected, it's connected. Make sense? And a lot of the ways that we're going to be proving things are connected is we're going to think about it in terms of assume by way of contradiction that it's disconnected. Because disconnected is what gives us the information, right? Kind of like, how do we prove a set's closed? We show its complement is open. That's how we show it's closed. Kind of like that. Okay, so that's what it means for it to be disconnected. It's connected if it's not disconnected. And then finally, if X is disconnected, we call the sets U and V that you used to show it was disconnected, this U and V, a separation of X. So what's a separation of X? It's two non-empty open sets that have no overlap, but when you union them together, you get X again. It's the two open sets I can divide X into. Make sense?
Yeah.
All right. Let's look at some discrete examples just make sure. All right. So let's look at this topology and this topology. You with me? You remember how these pictures represent topologies and what the open sets are?
Somewhat.
Yeah.
So this is the set A, B, C. And what are its open sets? Well, the set containing B is open. The set containing BC is open. The set containing AB is open. And the set containing ABC is open. And then the empty set is open, which we don't draw.
Okay.
So this right here is shorthand for, well, I think you understood, right?
Mm-hmm.
Okay. So question, is this connected or disconnected? The whole space.
Connected.
Connected. There are no two open sets I can find that split X up into two open sets. I can't split X up into two open sets and have them not be empty. You might think, can I split it up into the set ABC and the empty set? Those are two open sets. Yeah, but they're not two open sets that aren't both empty.
Right.
So that's why we have this property here, that they can't be empty sets. Otherwise, every single topological space would be disconnected.
Right.
Because we could always just use the whole space in the empty set. Okay, what about this one? Is this connected or disconnected?
Disconnected.
Disconnected, right? And what are the two sets?
AB and CD.
A, B, and C. Those are both open sets. Their union gives you back the entire set, and their intersection is empty. Make sense?
Mm-hmm.
That's all there is to it. Now we're going to do a lot with this, but we're just going to be working with this property over and over again and proving things about this property. Connected and disconnected sets. That's all this is about. Okay, so let's do some other examples. let X be the open interval from -1 to 0 union with the open interval from 0 to 1 as a subspace of R. So here's our set, and it inherits the standard topology from R. With me? And here's what it looks like pictorially. Is that thing connected or disconnected?
Disconnected.
Disconnected. Obviously, right?
Yeah.
Because our two open sets are that set and that set. Those are two disjoint, non-empty open sets whose union gives you back all of X. Okay. So I think that this pictorially makes pretty good sense for you when it's connected versus disconnected. Yeah, we'll just continue. Another example. So let's look at some topological space X where X has more than one element in it, and we'll give it the discrete topology. So X has more than one element, and we give it the discrete topology. Is that connected or disconnected? Do you remember the discrete topology?
No.
The power set of X. Do you remember what the power set is?
All possible subsets.
All possible subsets.
So it's
So one in it would be disconnected.
So it's disconnected, yeah.
Oh.
Huh?
Oh.
1. Let A be a proper subset of X. You know what proper subset is versus just subset, right?
Means it can't be equal.
It's not all of X, but it's some subset of it.
Okay.
Since, A be a proper subset of X where A is not empty. And notice that since X has more than one element, then such a set exists. I can find a non-empty proper subset of X, right?
Yeah.
2. Then A and A complement are a separation. Is this set open?
Mm-hmm.
Is this set open?
Yeah.
Do they have any elements in common? And when you union them together, what do you get?
X.
All X.
Okay.
Any questions on that example? Cool. What's next? Next example. X with the trivial topology. You remember what the trivial topology is?
Isn't that just the empty set and then the whole, then all of X?
Yep. Tau is equal to X in the empty set.
So it's
Oh, yeah.
connected.
It's connected. Doesn't matter what your set X is, if your topology is a trivial topology, it's always connected. I can't split that thing into two open sets that aren't empty. Make sense?
Yeah.
Yeah.
Okay, next. So we're going to look at R with 1 point removed. We've got R, subtract 1 point with the standard topology. Is that connected or disconnected?
Disconnected.
Disconnected.
Makes sense for it to be disconnected.
Yeah, it's disconnected. Here's P. So we've got the whole number line except for this point, right?
Yeah.
So you've got all the numbers over here and all the numbers over here. Are all the, in other words, this set right here is the same thing as negative infinity to P union P to infinity. There's your two sets that are non-empty that show that it's disconnected, right?
Okay.
Okay, so hopefully those examples help your intuition a bit about what we mean by connected versus disconnected. So let's do a quick theorem. So we're going to prove that some topological space X is disconnected if and only if it contains a non-empty clopen. You remember what clopen is?
Closed
No.
and open.
It's a set that's both closed and open.
Okay.
Yeah, it's clopen. So some topological space is disconnected if and only if it contains a non-empty clopin proper subset of X. So if it contains some set that's both closed and open, that's not empty, and that isn't all of X, then the space is connected. That's what we're disconnected. Thank you. Disconnected. So it's disconnected if and only if it contains a clopin set that's not empty and not all of X. Make sense?
Yep.
Alright, so let's prove it. We're going this way first, I guess. So let X be disconnected. What does it mean for X to be disconnected? It means that there exist two open sets U and V that aren't empty, two non-empty open sets whose union gives you X and whose intersection is empty.
Mm-hmm.
With me?
Mm-hmm.
Okay, so then notice that U complement is equal to V. Everything in X that's not in U must be in V. Because their union gives you all of X and they don't have any elements in common.
Why didn't in their definition just say U and U complement then?
Because they wanted.
Why didn't they in their definition say U
Not
and U
in your
complement?
proof, but in your definition 6.1. Like,
Say,
if
why
that's
did
what
you-
you're
This
saying.
set does not have to be the complement of this set.
But the complement plus the set equals X.
We'll see in the subspace topology, when we look at subspaces topology, like this picture over here.
Okay.
You'll notice that U and V have an intersection here, and yet they're still going to show that the subspace, the subset A, is disconnected. Well, we'll get to it, and you'll see
Okay.
why that wasn't in the definition. Okay. So U and V union together gives us back all of X, and they don't have any elements in common, so that means U's complement is V. U's complement, which is equal to V, is open. We know that V is open, right? So I just barely showed that U's complement is open. And since U's complement is open, U is closed. What does it mean for U to be closed? It means its complement is open. So U is open and closed. So that's our set. Therefore, U is clopin.
Okay.
And it's not empty and it's not X. Okay. So now let's go the other way. Let U be some non-empty set that's clopin and assume it's a proper subset of X. Then let V equal U's complement. So then V equal to U's complement is open. How do I know that V is open? Because U is closed.
Yeah.
So its complement is open. So I know that V is open, and I know that V is not empty. How do I know that V is not empty?
Because
Because it's
U
equal.
isn't all of X.
Perfect. U is a proper subset of X. So V is not empty. Wonderful. So then I have U and V are sets that aren't empty. U and V are non-empty sets. That's all we're saying here.
Mm-hmm.
U intersect V is empty, obviously, because V is the complement of U.
Right.
And U union V is all of X, obviously, since V is the complement of U. Therefore, X is disconnected. Feel like you understand that proof?
Yeah.
Cool. Example, R with the lower limit topology. Okay, so let's remind ourselves what the lower limit topology is. The lower limit topology is the topology we get on R where our basis elements look like this. So any union of things that look like that are open sets. Question, is that set is that topology connected or disconnected?
Lower limit topology?
Yeah.
Disconnected.
How do you know?
Because it's clopin.
Yeah, because a basis element is open and closed. Does that make sense?
How is it closed? You have to union.
What's the complement of something like this?
Well, it would go from V to infinity and then.
You get negative infinity to A, not including A. And then you get including B to infinity. Both those are going to be open sets. Union them together as an open set.
Okay.
Does that not make sense?
Not really.
Uh,
How is negative infinity like closed on the left side? Like
Negative
it's like that basis
infinity to A, like that.
only?
So you're saying how is this open in
Yeah,
this
how is
topology?
that open?
You can union up it's going to be an infinite union, and you can union up A minus 1 to A, union with A minus 2 to A minus 1, and continue in that manner, and union up all infinite of those. And you'll go back infinitely far.
Okay, I see now. I forgot that you could do infinite unions and stuff.
Yep, infinite unions. Any union of basis elements, we can union up infinitely many things that look like this to create this set, right?
Mm-hmm.
All you do is make sure you start right at the end and then go back. Just make sure you're taking some incremental step back and eventually you get infinite. Okay, so does it appeal to our intuition that this is open and closed?
Yes.
Mm-hmm.
Alright, so we found some open and closed set. Therefore it's connected. Or disconnected, sorry. Therefore it's disconnected. Well, we found some open and closed set that wasn't all of X or the empty set. Okay, next. Right here. Okay, the set A as a subset of X is said to be connected in X. So A is a subset of a topological space X. Should have specified that. A is a subset of a topological space X. It's said to be connected in X, provided that the subspace topology on A is connected. So take A as a subset of X. You've got all of X. Take a subset A. Give it the subspace topology. We call A connected if when you give it that subspace topology, it's connected topology. It's almost exactly what you would have guessed this definition saying.
Can you remind me what a subspace topology is?
Yeah, what are the open sets in a subspace topology? What are the open sets in A? It's all the open sets in X intersected with A. So if we're talking about in R, how far over here can I see? I just realized I'm drawing over there. Oh, yeah, I meant cover all this and then move the phone on that cover so I can see all this. Okay, what were we talking about? Subspace, open spaces in a subspace. So let's look at the subspace negative, we'll just draw it on the number line actually, what the numbers actually are. So here's R, we'll look at subset in R. Here's some subset in R. And we're saying about the standard topology. So R has a standard topology, so open sets in R, just open intervals. And then here's just a subset in R. With me so far?
Yeah.
Now if we want to turn this subset into a subspace, we need to give it a topology. What are the open sets in here? This set right here, A. What are the open sets in A? Take any open set in R. Here's an open set in R. Now intersect it with A. And whatever you get is open in A. So this interval is open in R. When we intersect that with A, we get this thing is open in A. Does that make sense?
Yeah.
So that's how we define our open sets in a subspace topology. So I want to know, or no, by definition, so I'm looking at the set A as a subset of R. And I ask the question, is A connected in R? That's the same question as, is the subspace topology on A connected? Is A connected in R? Is the subspace topology on A connected? Those are asking the same question. That's what this definition is saying. Let A be a subset of X. No, that's what we're proving, sorry. The set A in X is said to be connected in X. Not proving. It's a definition. Sorry. Okay. So the set A as a subset of X is said to be connected in X, provided that the subspace topology on A is connected. Otherwise, A is disconnected in X. So every subset of X is either connected or disconnected. How do you determine if it's connected or disconnected? You give it a subspace topology and look at the topology and see if it's connected or disconnected. That's it.
Okay. If you were to look at it though, how can you tell if it's disconnected then?
If you were to look at it,
You said if you take the subspace topology on the set and you were to look at it, then it will either be connected or disconnected.
yeah, it has to be one of those. You have to prove what it is.
Oh, okay.
But you know it's one of them. So if you prove that it's connected, then it's not disconnected. If you prove that it's disconnected, then it's not connected. I'm saying it has to be one of those two, though. Okay, so we understand this definition? Alright, so quick example. Let's look at A equal to this as a subset of R with the Theorem topology. Is that open or closed? Or sorry, is that connected in R or is that disconnected in R?
Disconnected.
Yes, A is disconnected in R. Why? Because a subspace topology is disconnected. Here we were talking about a subspace topology. Here we were talking about A as a subset of R. This topology over here was disconnected. So A is disconnected in R. They're almost saying identical things. Make sense?
Mm-hmm.
Okay. Next definition. Let A be a subset of X if U and V, if there exist two open sets such that A is a subset of their union. Okay, let's look at the picture and then go over this definition because there's a lot of sets and it's going to be easy to get confused. Here's what we're going to say. We're going to say, so here's X, this whole set, and it's got some topology. Here's A. Notice it's split in two places. So all these points union all these points is A. A is just some random subset of X. And then U is an open set and V is an open set. Here's what we're going to end up saying. We're going to end up saying that U and V are a separation of A in X. So before we were talking about just a separation on a topological space. We're going to say that U and V are a separation of A in X. It's only changing our terminology. Because now we're talking about subspaces. So let's read it exactly, and this picture is going to make sense to you. Here's what we're going to say, essentially. U is an open set that intersects A. So U and A's intersection isn't empty. V is an open set that intersects A. So its intersection is empty. U, notice that A is a subset of U union V. And notice that everywhere that U and V intersect is outside of A. So everywhere that U intersects A is separate from everywhere that V intersects A. And so U and V are going to be a separation of A on X. Or in X.
U and V don't have to intersect, right?
They don't have to intersect. They just couldn't. So this is going to be a perfectly valid picture for what we're talking about. This is also going to be a perfectly valid picture for what we're talking about. The point is, what U and V do outside of A is irrelevant to us for using them as a separation.
As long as A is divided, is that what you're saying? As long as A is separated.
This is how we're going to say that A is separated. That A is disconnected in X. We're going to say that's going to be the next theorem, but first we need the definition. So we're going to say that this set A is separated in X. And how do we know? Because we were able to find two open sets U and V such that we can split A so that part of A is in U and not in V, and part of A is in V and not in U. And we don't need to be tricky and find a perfect U that doesn't intersect V, a perfect U and V that don't intersect. We don't need to make it hard on ourselves. We don't need to find U and V that look like this. But we can be lazier and let them intersect, and we can still use this idea. So here's what our picture's going to look like. Let's read the definition exactly now, and then see if it makes sense. So let A be some subset of X. If U and V are open sets, such that A is a subset of their union, notice union U and V, A is a subset of it. So all of A is in U and V. Okay. So U and V are open sets such that A is a subset of them. U intersect A is not empty, so sum of A is for sure in U. V intersect A is not empty, so sum of A is also for sure in V. So not only is A completely in U and V, but sum of A is for sure in U, and sum of A is for sure in V. That's what these are saying. And U intersect V intersect A is empty. In other words, inside of A, U and V don't intersect. They might intersect outside of A, who cares? Inside of A, U and V don't intersect. U and V might intersect out here, who cares? Inside of the set A, U and V never intersect. So it's a picture that is not like this. If we carry this over like that, and then like that, okay, now that's not true. This would be a bad picture for what we're talking about. Good picture is making sure that this doesn't get inside of A over there. Okay, so if those conditions are met, then we say that the sets U, V are a separation of A in X. A lot of symbols, but I think the idea is pretty clear. We just divided A into two open sets again. That's all we really did.
Okay.
Where there's no overlap.
So what's the theorem proving?
Okay, so now here's what we're proving with the theorem. We're going to say that the set A is disconnected in X if and only if there exists a separation of A in X.
And is that what you call separation?
This is a separation of A in X. So if there exist two open sets, U and V, satisfying these properties, then A is disconnected. And if A is disconnected, then there exist two open sets, U and V, satisfying these properties. That's what we're doing. Feel like you understand?
Yes.
All right, let's go through. So 1, let A be disconnected in X. So what does it mean for A to be disconnected in X? It means that there exists U and V with all these properties here. So then the subspace A is disconnected. Wait.
Oh, you said let A be disconnected.
Oh, let A be disconnected. So we're going to prove that these properties are there. So if A is disconnected in X, that is this right here. The set A is a subset of X is said to be connected in X, provided that the subspace topology on A is connected. So what does it mean for A to be disconnected in X? It means the subspace topology on A is disconnected. With me? Okay. So let A be disconnected in X. So the subspace topology is disconnected. So then the subspace A is disconnected. What does that mean? That means that there exists two open sets in A, not open sets in X, open sets in A, call them U prime and V prime, such that they're not empty. When you union them together, you get A, and when you take their intersection, it's empty. Good so far? These are open in A, not open in X.
Right.
Okay. Since U prime and V prime are open in A, what does it mean to be open in A? It means that they can be expressed as an open set in X intersected with A. So since U and V are open in A, then there exists U and V. Since U prime and V prime are open in A, then there exists U and V open in X, such that U prime is equal to A intersect U, and V prime is equal to A intersect V. That's what meant to be an open set in the subspace topology. When is a set open in the subspace topology? When it's a union, when it can be expressed as an intersection of an open set and the subset that you're putting the topology on.
Right.
Exactly what we were drawing in this picture down here. How do I know that this set is open in A?
Could you combine?
Because I can express it as the intersection of this set with A. If I can write it as an intersection of an open set in R, or we'll call this X, even though it's R in this example, it's X for our proof up there. If I can find an open set in X such that its intersection with A gives me that set, then the set we're talking about is open. That's an if and only if. That's our definition of an open set in a subspace topology. So since I know that U prime, right here, since I know that U prime is open in A, it means that U prime is equal to A intersect some open set in X. The way that I know that this is open in A is I know that it is equal to some open set in X intersecting with A.
Okay.
Am I saying that too much? Okay. So then U prime can be expressed as A intersect U, where U is open, and V prime can be expressed as A intersect V, where V is open. Right? Well, then UV is a separation of A and X. In other words, UV has all these properties. So let's go over each of them so make sure that you can see it. Is A a subset of U union V?
Yeah.
Yes, because U prime union V prime gives us A. Sorry, up here. U prime union V prime gives us A, and U is bigger than U prime, and V is bigger than V prime.
Right.
Right? So, yep, we've got that. Let's see. Is U intersect A not empty? Yes, because U prime is not empty. And this is U prime.
Yeah.
So we know U prime is not empty. We know V prime is not empty. And then U intersect V intersect A. Is that empty? How do we know that U intersect V intersect A is empty?
Because
Well, we don't.
U prime intersect with V prime is empty.
Perfect. This is U intersect V intersect A. That's what this is. And it's empty. Okay. So there we go. UV is a separation of A. Now let's go the other way. So next, let U and V be a separation of A in X. And then we'll define U prime to equal U intersect A, and we'll define V prime to equal V intersect A. Notice that U prime and V prime are not empty. How do I know that?
How do you know that?
Because U and V are a separation of A, U and V have these properties. I know this about U and V, I know this about U and V, I know this about U and V, and I know this about U and V. That's what it meant to be a separation of A in X. So since U and V are a separation of A in X, then I know this is true, because I know that this isn't empty and I know that this isn't empty. U prime intersect V prime is the empty set. How do I know that? U prime intersect V prime, once again, is the exact same thing as U intersect V intersect A. U prime is U intersect A. V prime is V intersect A. So this whole thing is U intersect V intersect A. It's everything that's in U and in V and in A. So that's empty. And then, since A is a subset of U union V, then A is equal to U union V intersect A.
Yeah.
You follow that?
No,
Let's do that one more time. Everything in A is in both those sets. Right? So if I take everything that's in both those sets and in A, I just have A.
Yeah.
Okay. that's all we were seeing up to there. But now notice that this is exactly what these two sets are. Probably could have drawn one more line up here. Let me draw one more piece of logic here. This is equal to U intersect A union U V intersect A
Oh, yeah, that would look very.
is equal to U prime union V prime. Sorry. Running out of space. So A is equal to U prime union V prime. That's a V. Good?
Yeah.
And therefore, A is disconnected. We found two open sets in A such that they were non-empty, their union gave you A, and their intersection was empty. Any questions? Cool. Then let's move the phone. Okay. Next, we're going to prove that continuous functions preserve connectedness. So if you have a connected topology and you run it through a continuous function, the result is still a connected topology. Make sense? That's high level what we're going to prove. So let's read it exactly now. If X is connected, a connected topological space, and if F from topological space X to topological space Y is continuous, then F of X is connected in Y. Because F of X might not be all of Y. So what we're saying is, if you look at F of X as a subspace of Y, it's for sure connected. And if F of X happens to be all of Y, then Y is connected.
Can you remind me what it means for a function to be continuous?
What is it, Leah?
It's the one where it's like the image of
Or before the image.
pre-image is open. Something like that.
The pre-image is open. The pre-image of what?
Pre-image of Y. The pre-image of the set. I don't know.
What is it,
Something
Emma?
like that.
The pre-image of open sets are open.
The pre-image of open sets are open. Take an open set of Y, look at its pre-image. Its pre-image is going to be some set in X, right?
Mm-hmm.
That set is open.
Okay.
That's what it means for a function to be continuous. The pre-image of open sets are open sets. The pre-image of open sets in Y are open sets in X. Keeping track of which way the function goes, then the pre-image goes the other way, right? Anything weird about that? Feel like you understand?
Yeah.
Okay. So, we're going to prove that if X is connected, then F of X is also connected. And does it make sense to you that F of X is not necessarily all of Y?
Yeah.
Perfect. And what would be the topology on F of X then?
Well, it would just be all the open sets in Y intersected with F of X.
Yeah, it's the subspace topology it gets in Y. So if we have X is this space, Y is this space, F maps like this, but maybe F of X is just this. Maybe when you map X, you only use up this much Y. Now F of X is a subset of Y, right? And so what's the topology that we're talking about in F of X? We're talking about the subspace topology that it gets from Y. Take open sets in Y, intersect them with F of X. Those are the open sets we're talking about. Make sense?
Mm-hmm.
And then if F of X happens to be all of Y, then we're just saying Y itself is connected. So in other words, if F is continuous and on 2, then Y is connected.
I have a question. With a continuous function, is the pre-image of closed sets closed?
Is the pre-image of closed sets closed? I want to say yes. It's either that or the image of closed sets is closed. I think it's the pre-image. The pre-image of closed sets are closed. I think that's right. Because, yeah, if you look at the pre-image, take a closed set in Y, then its complement is open. So then the pre-image of its complement is open. So the pre-image of what you start with has to be closed.
Yeah, that's how I was thinking of it, but, alright.
Yeah, that's essentially how you prove it, I think. I know that we did prove whatever it is, and I think that's what we proved. Anyways. Where are we? Oh, so we're doing this proof. Okay, so if x is connected and f is continuous, then f of x is connected in y. That's what we're proving. Understand what we're proving? Ready to continue? Mm-hmm. Okay, so remember, when you're trying to prove something is connected, since we don't really know what to do with connected, we just know what to do with disconnected. It's very common that we assume by way of contradiction that the set is disconnected and show that leads to an impossibility, and therefore it's connected. That's almost always how you do proofs that some topological space is connected. And you're going to see that we do that like 3 times from here on out. So let's go through it. Assume by way of contradiction that f of x is disconnected. Well, if x is disconnected, or if f of x is disconnected, then there must exist some separation uv in y. Some separation of f of x with the sets uv in y. So it has to be 2 open sets u and v and y that give us a separation on f of x. Sorry, I said that weird, but I'm talking separation just like this.
Yeah.
U and v are a separation of f of x in y. So they have these properties. With me? Okay. Now, let u prime equal the preimage of u. So u prime is in x, and notice it's going to be open in x, since f is continuous. And let v prime be the preimage of v. V prime is also going to be an open set in x. I'm going to show that u prime and v prime are a separation of x, and therefore x is disconnected. Contradiction. That's going to be my contradiction. How am I showing that x being connected implies f of x is connected? I'm going to assume by way of contradiction that f of x is not connected, and show that leads to x not being connected. Contradiction. Big picture, that's what we're doing. So we're going to let u prime be the preimage of u, and v prime be the preimage of v, and we're going to show that these 2 things are a separation on x.
Okay, so yeah.
Okay. So let u prime be the preimage of u, let v prime be the preimage of v, and observe that u prime and v prime are open in x, because f is continuous. What does it mean for a function to be continuous? The preimage of open sets are open. So u prime's open, and v prime's open. Now, since f of x is a subset of u union v, how do I know that?
Because it's a separation.
U and v are a separation of f of x. So their union has to give us back all of f of x. So since u and v, or since f of x is a subset of u union v, then x, the preimage of f of x, has to be a subset of the preimage of this set, which is u prime union v prime.
It kind of feels like you're assuming that f of x and y are the same. Like you said, there exists a separation uv and y, like u and v are in y, but then you're saying you can take the preimage of u and v. They might not be in f of x.
Ooh, they're always in there. It's just that they might not have been mapped to from x, so they go to something empty.
The preimage of something can be empty.
So, yeah, I can look at the function 1, 2 to the set a, b, c, and map 1 to b and 2 to a. I can still say that the preimage of a, b, c is 1, 2. It doesn't matter that c wasn't mapped to from anything.
Okay, alright.
So, yeah, it's perfectly fine that there's elements in here that weren't mapped to.
Okay.
Okay. So since f of x is a subset of u union v, then the preimage of f of x is a subset of the preimage of u union v. With me on that? Okay. Oh, that's the picture we just drew. Since u intersect v is empty, how do we know that?
Because there is separation.
Because they're a separation. It's a property of them being a separation. So since u and v are empty, then u prime and v prime have to be empty. Does that one make sense?
Wait, U intersect V is empty,
Because it's a separation.
but I thought they could have elements together. U intersect V.
That is a wonderful point. So since, now I lost where we were.
5.
Since u intersect v intersect f of x is empty. Good catch. U intersect v intersect f of x is empty. That gives us u prime intersect v prime is empty.
How do you know that u prime and v prime are empty?
So assume that they had a common element a.
Okay.
Well, everything u maps to is in, everything u prime maps to is in u and not in v. Everything v prime maps to is in v and not in u. If they had a common element a, then f of a would be in both these sets. That's impossible.
Gotcha.
These two sets are disjoint in f of x. If the element came from x, these two sets are disjoint. That's another way to make sense of that. Does that make sense?
Mm-hmm.
Okay. Alright, and then finally, since u intersect f of x is not intersect, or is not equal to v intersected f of x, is not equal to the empty set. In other words, since this is non-empty and this is non-empty, then their preimage intersected with x is non-empty.
Right.
I don't know why I'm intersecting with x. I just need to say their preimage is non-empty. The preimage of u is not empty, and the preimage of v is not empty. So, u prime, sorry. No, I said that right. The preimage of u is not empty, and the preimage of v is not empty. Okay, yeah, that's right. So, u prime and v prime are open sets in x, they're not empty sets, and their union gives us back x.
I thought X was just a subset of their union. That's all you have written.
F of x is a subset of their union.
So X.
So the preimage of u and v has to contain all of x. All of x was mapped into u and v. So if I take the preimage of u and v, I for sure have all of x. So
Yeah.
u prime union v prime is for sure x. I said subset here, but it's equal to because it can't be more. Because our domain is just x.
Okay.
So yeah, I should have just put an equal there. Any other questions about going this way? Oh, no, this is a
Yeah, it's
if
not
no.
an if no.
Well, just making sure.
Therefore x is disconnected. Oh, and therefore f of x is connected. So there's our contradiction. Therefore the opposite of what we assumed. So the whole trick was finding u prime and v prime in x such that these two sets are open, they're non-empty, their union gives you x, and their intersection is empty.
Yeah.
Why does saying X is disconnected gives you F of X is connected?
We already know x is connected. We're trying to show that that implies f of x is connected. We assume by way of contradiction f of x is not connected,
Okay, I see.
which led to x being not connected. Contradiction. Therefore f of x has to be connected. And that's important because we said if a set is not connected, then it's disconnected. Those are contradictions of each other, so it has to be one or the other.
Could we have gotten to our contradiction by saying that if there's a clopin set in f of x, then there would be a clopin set in x, and then you just have your contradiction there?
Ooh, if there's a clopin set in f of x, then there's a clopin set in x.
And that's why I was asking if the
But how do we
sets are
find there's a clopin set in f of x?
Well, you're assuming by way of contradiction that f of x is disconnected, and that's an if and only if. Like, that's equivalent to there being a non-empty clopin
That's true.
proper subset of f of x.
Assume by way of contradiction that it's disconnected. If it's disconnected, then it has a clopin set. The preimage of a clopin set is clopin.
So that would make.
I think
X
that works.
disconnected.
Yeah, that's a lot easier proof.
It just seemed too easy to me, which is why I was questioning if the preimage of closed sets are closed. But you said that's true.
You know what? That is worth double checking. Because I like that proof. Let's see. We talked about continuous functions. That was chapter 4.
Yeah, I don't know.
Homeomorphisms. Yeah, we do have that. Let x, y be topological spaces. A function f from x to y is continuous if and only if the pre-image of a closed set is closed.
Well, that really simplifies that proof.
Yeah, it does. Assume by way of contradiction that f of x is disconnected. Oh, here's where we're going to get stuck. F of x is disconnected in y. So we have a clopin set in the subspace topology, but we need to be clopin in y. So we'd have to go from it being closed and open in f of x to being closed and open in y, which isn't necessarily the case. So if f was on 2, though, then we could use that. So it's a good thought, but it doesn't quite work. Because all we know is that there's an open and closed set in the subspace topology on f of x. There might be a way to still work with it, but it's not as trivial as we were thinking.
Okay, that makes sense.
Okay. We finished that. No. Homeomorphisms preserve connectedness. So notice we said all you need is a function to be continuous for it to preserve connectedness. So obviously if f is a one-to-one and onto function from x to y that's continuous and its inverse is continuous, then y is going to be connected. Because all we need is f to be onto for y to be connected. If f is one-to-one and onto and its inverse is continuous, and it's giving us way more than we need to conclude that y is, connected. So, this connectedness is a topological property, and it is another topological property that is preserved by homeomorphisms. So this is another way that you could quickly check to make sure that two topologies aren't somehow the same. If one's connected and one isn't, you're done. They can't be the same. Because remember, that's the hard part about showing that when you're dealing with topologies. It's a lot easier to show that they are homeomorphic than that they're not homeomorphic. Because to show that they are homeomorphic, we just need to find one homeomorphism and we're done. We need to find one function from one to the other that's a homeomorphism and we're done. How do we prove that no such function exists? That's much harder. And so the way that we do that is we need to show that, the typical way to do it is we need to show that one topology has a property that another topology doesn't have. And therefore they're not somehow the same. So one of the topological properties we already talked about was Hausdorff. Another one that we briefly mentioned was I'm not even going to try to say it. You can put a metric to induce a topology. And now we're talking about connectedness. That's another topological property. Okay, so homeomorphisms preserve connectedness. Okay, next, quick lemma that we're going to use a couple times for the remaining groups. So let C and D be subsets of a topological space X, and assume that C is connected, and that C is a subset of D. So C and D are subsets of X, and C is connected. So C is a connected subset of D is a subset of X. With me so far?
Yeah.
We're going to prove that if U and V are a separation of D, U and V split D, then our connected set has to either be entirely in U or entirely in V. It can't be in both. So you can't find a separation of a connected set, in other words. If a set's connected, that means there is no separation of it, right? That's kind of what exactly we're saying here. If U and V are a separation of D, then C, the connected set, has to be entirely in U or it has to be entirely in V. With me? Should be pretty intuitive. The proof's real small. Alright, let's go over it. Assume by way of contradiction that C is not a subset of U and C is not a subset of V. Should have mentioned right out the door, we're kind of ignoring the case. Obviously, C can't be a subset of both of them because U and V are disconnected, or because U and V are disjoint. So I'm kind of ignoring that, saying that's obvious, and not even thinking about that. Okay. So we know that C can't be a subset of both. I'm saying C has to be a subset of U, or C has to be a subset of V. So assume by way of contradiction that it's not a subset of U and it's not a subset of V, and we're going to get a contradiction. Okay? So then, C intersect U is not equal to the empty set, is not equal to, how can I make sure that this makes perfect sense?
You're just saying there.
U and V together give us D, and C is a subset of D. So if C isn't entirely in U, and C isn't entirely in V, then it's split between them. Some of C is in U and some of C is in V. So we're assuming by way of contradiction that we were somehow able to separate C into two different sets, U and V. You with me?
Yeah.
Okay. So C intersect U is not empty, and C intersect V is not empty. Then U and V, UV is a separation of C. Contradiction. C is connected, we just barely split it into two open sets whose intersection is empty, and such that their intersection with both of them was not empty. That's impossible. C is connected. So you can't separate a connected set. That's what it means to be connected. No separation exists. Right?
Okay.
Very straightforward. Therefore, C is either a subset of U or C is a subset of D. Let me just draw this one out really quick to make sure that we're good. So I've got D is some set, and C is some set inside of it. C is connected. So if I can find a separation of D, U and V, that wasn't a separation, we'll just, easier to just restart. Here's D, here's C inside of it. If I can find some separation of D, some way to split D into two open sets, C has to be entirely in one of the open sets or entirely in the other. We can't split C into two open sets because C is connected. There's no way to split into two open sets.
You're off the phone right now.
No, we can see this.
Yeah, he's good.
I'm from there to here. That's all we're saying over there. Should be pretty intuitive. C is connected, you can't split into open sets, even if it's a subset of some other set. Okay, so theorem. Let C be connected in X and let A be a subset of X, such that C is a subset of A is a subset of, what's that?
C complement.
Not complement.
Oh,
Okay,
is it
it's like
closed?
the closed set that like contains.
Closed. It is closed, but that's a property that set has.
It's either the union or intersection of all the complements.
It is the intersection of every closed set containing C, and we call it the,
Oh, that's.
it's not the interior,
The exterior.
it's not the exterior, the closure of C. Alright, that's not good. Because if you don't recall that off the top of your head, then you probably don't recall proposition 2.6, which we use over and over and over again.
I'm doing that.
Yes, it's the one I mentioned more than any other. It was an equivalence one, and I said you think about it as contrapositives a lot of the time, or how it is, so memorize it both ways. Because it's going to come up over and over again, and it never stops.
Yeah.
Well, here's a continuation of it never stopping.
Okay.
What did it say in short? Can you draw it over here? So, here's some set A. Notice it doesn't necessarily include its whole boundary. Right? And then you know what the closure of A would look like in R2, would include it. We say a point X, X is in A's closure, X is in A's closure, if and only if every open set containing X, every neighborhood of X intersects A.
Yeah.
Yeah.
The other way to say that is X is not in A's closure if there exists some open set containing X that doesn't intersect A. We'll be using that version. We'll be showing that since we can find an open set containing X that doesn't intersect A, X is not in A's closure. So here's what we're going to do when we do our proof by contradiction. We're over here. We're going to find a point in A that has an open set containing it that doesn't intersect C. Therefore, that point is not in C complement, or not in C's closure. Contradiction. We're going to find a point X in this set A that is not, let me change my picture over here. This is going to be our C, and then C's closure is going to be including the whole thing, right? For our contradiction, we're going to find some point A, some point X in A. So X, whatever that point is, we also know it's in the set A. We're going to find an open set containing X, where X is a point in A, that doesn't intersect C. Which means that X is not in C's closure. But A is a subset of C closure. Contradiction.
Gotcha.
That's our logic we're going to be using up there and how we're going to be using this theorem.
Okay.
So that's how we're going to get our contradiction. Okay. So let C be connected in X, let A be a subset of X such that A is sandwiched between C and C's closure. Then A is connected in X. So if A if C is connected, and A is sandwiched between C and its closure, then A is also connected. Another way that we can think about this is once a set is connected, if you give it its limit points, it's still connected. So you can keep adding points clear until you get C closure, and it's still connected. So for any subset between them, it's connected. Add 1 point, still connected. Add 2 points, still connected. Keep adding points clear until you get C closure, it's still connected. Even when A is C closure, still connected. Okay. So, assume by way of contradiction that A is disconnected in X. So, if A is disconnected in X, what does that mean? That means that there exists a separation on A with the sets UV. Right? Observe that C is a subset of U, or C is a subset of V, using what we just proved over
Yep, that
here.
lemma.
Yeah, that limit. So C has to be in one of those two sets. We'll call whatever set it's in U. So assume C is in U. If it happened to be in V, relabel your sets. So now C is in U. Doesn't matter. We're just going to call the one that C is in U. Let X be any point in A intersect V. Notice that C is a subset of U. Right? U and V give me a separation on A, so they're both non-empty when you intersect them with A. So pick some point X that's in A, intersect V. I know that there has to be some point, since U and V give me a separation on A. With me?
Yeah.
Okay. Then, X is in V, where V is open, and V intersects C is the empty set. How do I know that? C is a subset of U, and U and V are a separation. So V is my open set here, V containing X, that doesn't intersect C. There's my contradiction. So then X is in V, where V is open, and V does not intersect C. Therefore, X is not in C closure. Contradiction. Why is that contradiction? Because X is in A. Make sense?
Yeah.
Awesome. Therefore, A is connected. Good?
Yeah.
Okay. So, and notice that that means that the closure of any connected set is also connected. Any set between a closed set, any set between a connected set and its closure is connected. Therefore, the closure of any connected set is also connected. That's the important property that we get from that. Closure of a connected set is connected. All right, next theorem. Next theorem, how can I say this theorem in a high-level way so it makes perfect sense? If I have a bunch of connected sets that all have a point in common. So I've got a bunch of connected sets that have this point. Then the union of all those sets are connected. That's what we're going to prove. Okay, so let this collection of sets C sub alpha for a bunch of alphas in some set A. I don't know why I did the A in there. I must have need to reference it later. We usually just do C sub alpha. But C sub alpha for a bunch of alphas in A, those are just a bunch of indexes. This could be infinitely many, that's why we're not just using n's. So let that be a collection of connected sets in X such that their intersection is non-empty. There's a point in all their intersections. They have a point in common. Then C equal to the union of all those sets is connected. That's what we're proving. With me?
Mm-hmm.
Okay, so assume by way of contradiction that C is not connected. What does it mean for C to not be connected? That means that there exists a separation of C with the sets. We'll call them U and V. U and V are open. Let X be any point in the intersection of all our connected sets. I know that their intersection is not empty, so they have to have some point in common. Let X be at least one of those points. And observe that X is in U or X is in V. Right? U and V are separation on the union of all the sets. So X has to be in one of those two sets. obviously can't be in both since there's separation. And we're just going to call the set that it happens to be in U. It has to be in U or V. If it happened to be in V, relabel them so now it's in U. Okay. Since X is in U, then for every alpha in A, C sub A is a subset of U. If X is in U, and every connected set has to be in either U or V, it can't be in both. X is in every connected set, X is in U, therefore every connected set has to be in U.
Okay.
Back to this lemma over here. Right here. If we have a connected set and a separation on a set that it's in, that connected set has to be entirely in U or entirely in V. So I know every C sub alpha has to be entirely in U or entirely in V. But since X is in U, then every C sub alpha has to be in U. Because X is in every C sub alpha.
Okay.
That make sense?
Yeah.
Therefore, C is a subset of U. Which means that C intersect V is the empty set. Contradiction. Right?
Yeah.
Because V was one of the two sets that gave us a separation on C, so it can't be empty when you intersect with C. Therefore, C is connected in X. Same basic logic we've gone over again and again. Alright, so move the phone one more time as we go to the whiteboard. Actually, will you move that over as far as you can and keep it on the whiteboard in case I need to scribble over there? Where did I put that blue marker? It was writing pretty good. Okay, next theorem. If X and Y are connected topological spaces, then the product space X cross Y is connected. You remember what the product space is?
Yeah. Takes all the left-hand elements from X with all the right-hand elements from Y, right?
That's X cross Y, but what's the topology it gives? What do open sets in X cross Y look like?
Open sets in X cross with open sets in Y.
No. That was our naive first attempt, and we showed why that led to a bad picture that we didn't like. Basis elements in X cross with basis elements in Y give us the cross product topology. If you do the cross product of basis elements instead of just open sets, then you're good.
Saying the cross product of basis elements are open or are basis elements?
Are a basis for X cross Y.
Okay.
It turns out that that's, I can't remember exactly how we define this, but that is an equivalent way of doing it. That's something that we proved down the road. But that's one that you always remember. Cross the basis elements. Anyways. Okay, so let's prove it. So let X, Y be connected spaces. Now, observe that for all little x and big X, little x cross Y as a subspace of X cross Y is homeomorphic to Y. This thing is homeomorphic to this.
How do you know that?
How do you know that? Because imagine I took R, and now I just crossed R with the set 1. Take the standard topology on R, now take the standard topology on R when you cross all your elements with 1. Does it change my topology in any way?
No.
No. It's the same thing.
Okay.
I mean, you're going to have, your map is just going to be f of x is equal to, we call this x over here, pretend I put x naught there to help you with the picture. We're going to do f of x, oh sorry, which way do we want to map? We'll map, I'll do a map from y to there to show you what the map will be. So we'll look at f from big Y to, we'll give that element an actual name, x naught, cross y by f of little y is equal to x naught little y. That would be my homeomorphism. Anything open over here is still going to be open over here. Anything open over here is still going to be open over here. Just look at how it maps basis elements. And you can even view this, if you want, as a way of picturing it. Let's not do that one. I'm going to say also this is a homeomorphism. F from x to x cross little y naught by the same thing. But this one, when I draw a picture for it, I think you'll get it. So if we were just doing, imagine that we're on R for a second, and x would just be R, and we're going to go to R cross some number. So here's R, that's right here. What do open sets look like in R? Open intervals like that, or unions of open intervals. Now let's look at R cross some y. That would give us something like right here. What do open sets look like here? They look like that. Same thing. Mapping them from here to here, or mapping them from here to here, doesn't change the topologies.
Okay.
That's all we're doing. Same topologies. We're just taking every point in the topology, and instead of just calling it 2, we're calling it 2 comma something. Instead of calling it x, we're calling it x comma y naught. It's like we're just relabeling all the points in the topology with, instead of just that, we're adding this onto it. Instead of just calling it x, we're calling it x comma y naught. It's just relabeling the points. It doesn't change anything. Make sense?
I think so.
That one should be pretty straightforward. That shouldn't be... I mean, you can prove this if you wanted.
I think I'm good.
Yeah. Obviously, 1 to 1 and 1 2, and then you just gotta make sure that it maps basis elements, and preimage to basis elements, and you're done. Anyways, we weren't doing that. We were doing this. So observe that for any x you pick, that little x cross y, as a subspace of x cross y, is homeomorphic to y. Good?
Mm-hmm.
Similarly, for any y you pick, x cross that y is homeomorphic to x. Good? Okay. Therefore, for any x and any y you choose, x cross y union x cross little y, hard to say it, but when you see it, I think it's pretty clear, is going to be connected in x cross y. How do I know that? How do I know that this is connected?
Because it's a homeomorphic.
This is homeomorphic to y. How do I know that this is connected?
Homeomorphic to x.
It's homeomorphic to x, and these two things always have a point in common. Right?
Yeah.
X comma y is always in both of these. Because this uses every y, this uses every x, so it uses this particular x, and this uses this particular y. So x comma y is a point in both those. If a point is in two connected sets, then the union of those connected sets is still connected. That's what we just proved. Right?
Yeah.
Okay. So then this is connected in x cross y. So now pick a particular x, we'll call it x naught. And now if we, for every little y and big Y, union up this union, so I already showed that this union was connected.
Mm-hmm.
Now I'm showing that when you union up a bunch of these unions, it's still connected. How do I know that this is connected?
We just proved it. Like this.
This, yeah, we know that this is connected from up here. And then when I loop over every y, how do I know that it's still connected?
Because of the one, that theorem that
They'll still have a point in every single one, right?
Right. They're still going to have now a common element in all of them from our y's. So pick that particular, if we draw out what this looks like, how can I draw this without making a mess? So we've got some x naught. I'll just use xy plane because I don't know another way to do it. So you've got some x naught. Here's x naught cross y if we look at two-dimensionally, right?
Yeah.
Mhm.
So this set and this set always have a point in common, namely x naught and some particular y. Doesn't matter. Same reason that these two always have a point in common. This is just a special case, right?
Yeah.
And now, when we union up across every y, we keep forcing ourselves to reuse this set over and over and over again. So now when we do that big union, they're always going to have a point in common. So overall, it always has a point in common. So we start out by doing this line union, this line, and then we do it this line union, this line, and then we do this line union, this line, and we keep doing that for all of these. And we're filling up the plane that way, unioning them all up. Doing it in such a way that we keep using this over and over again. So this and this always have a point in common. Same logic as we had up there. Now this and the next set, when you pick a different y, always have a point in common. Because we keep forcing the same line to be in all of them. Okay, think you got that?
Yeah.
So they all have at least one point in common. Therefore, they're all connected. And notice that when we do this unioning up, we're going to get all of x cross y.
Right.
Okay. And then, no reason that we need to prove it. It'd be real easy to do, but just a quick corollary. Now, if I have n connected sets, then their cross product is also going to be connected. And you just do a quick proof by induction with that. Because here's your base case. Assume it's true for k. Then it's true for k plus 1. How do you do that? You put your first k, union them together, that's one set. Your k plus 1 set is another set. That's just unioning two sets. You just use this again. So,
Makes sense.
quick proof by induction to show you can do it for n of them. Alright. Definition. Let x be a topological space, and let that tilde c, tilde sub c, be a relation on x, such that x is related to y with this relation, if and only if x and y are in some connected subset of x. If I can find a connected subset of x containing both x and y, then they're related. So we've got big X here is our whole space. We got little x and we got little y. These two are related if there is some connected set containing both of them.
Okay.
If there isn't, then they're not related.
If x is connected, then that means that they are related, yes?
Yes, if
Okay.
x is connected, then they are related. But furthermore, they're related if I can find any subset of x containing them. That's a connected set.
So x doesn't necessarily need to be connected.
X does not have to be connected.
Okay.
Okay. So now, really quick, we're getting all that this thing's an equivalence relation. Notice that x is always in the same connected set as itself, right?
Mm-hmm.
So x is in the same connected subset as x is always true.
Yeah.
Alright. Now, if x is in the same connected set as y, obviously y is in the same connected set as x, right?
Yeah.
Now, if x is in the same connected set as y, and y is in the same connected set as z, so x is in the same one as y, and y is in the same one as z, I know I can just union those together in its connected set, and it contains all three,
Right.
which shows transitivity. So this thing is an equivalence relation. Okay?
Makes sense.
An equivalence relation gives us equivalence
Class.
classes. Or in other words, it partitions up our set X somehow. Right?
Yep.
So we're going to call those partitions that this relation gives us components of the space. That's what a component is. It's an equivalence class that this relation gives us.
If X is connected, then is there just one equivalence class?
Yep.
Okay.
That's kind of tricky.
But it's possible, I mean, you could imagine for, let's just go to R2 real quick and look at subset of R2. I could have A is here, here, sorry, still A, I don't know why I put B. Let's say that A is this set. So that ball, and that ball. Then obviously A has 3 components.
Yeah.
Right? That's exactly what that's going to say. Because this little ball here is going to be connected. You can't take this little ball and divide it into 2 open sets. Does that make sense? And the problem there would be the boundary. Because if I try and take this open ball and I try and divide it into 2 sets, do the points right there go to that set or that set? So if I try and split this into 2 sets, I might try to split it like this. Is that the 2 sets I'm going to split it into? That's not 2 open sets. So I can't take in R2 an open ball and split it into 2 open sets. So a ball by itself is connected. But obviously this ball and this ball are disconnected. Make sense? So, since this ball and this ball are disconnected, then, we were doing down here. So if we look at the subspace topology induced on A from R2, then it's going to have 3 components. So components are almost exactly what you would think if you actually saw pictures in topologies that we're used to working with. Make sense? Okay. So, theorem. The components of some topological space X are connected. And that should make kind of intuitive sense. The component's going to be connected because you can kind of think about it as a union of a bunch of different connected sets, getting them as big as you can. Because what is a component? The component X is going to be the set of all points that I can find that are in the same connected set as X. That's going to be a component. So the component picks some representative element in there, that point. This component is going to be all the union of all the connected sets I can find containing that point.
Okay.
So components are going to be connected sets, which shouldn't be surprising because we kind of think about them as a union of connected sets.
And you're going to prove that?
Well, we're going to prove this. So the components of X are connected. That's what we're proving. So let's do it. Let C be any component of X and let little p be some point in C. Then for any other point, any could be the same, but for any point X in C, then we know that there exists some connected set Cx containing both X and P, right? X is in the same equivalence class as P if and only if there's some connected set containing both of them. Call that set Cx. So for any X you pick, call Cx the connected set containing both X and P. That's what Cx is. With me so far? So here's P. X might be here. We're going to say for every X in this component, there has to be some connected set, could be this set, could be the whole component, containing both those points. So first thing we need to make sure is that this C sub X is actually a subset of C. So for any X in C, blah, blah, blah. Observe that for any other point in C sub X, Y is in the same component as X, therefore C sub X is a subset of C. C was everything related to the point P.
Yes.
We know that X is related to the point P. Anything in Cx is in the same component as Y, or anything in Cx has to also be related to X. We know X is related to P. Therefore, anything in there called Y is related to X, X is related to P, therefore Y is related to P, therefore they're all in the same component that P's in.
Yeah.
So that whole set is a subset of C. Okay, that's the first thing we need to make sure. Now, we define C to be the union of all those CX's. Not define it. C is the union of all those CX's. That's the union lemma. I just barely showed that for any point in there, little x you choose, I can find a CX containing that point. That's a subset of C. Union all those up, that gives you C. That's just a union lemma. We've used that 100 times in this class. So that is a union of connected sets, so it's connected, since P's in all of them.
Yep.
Good? And then finally, one more definition. We call a set totally disconnected, provided that every single one of its components are just single element sets. Single element subsets of X.
Oh, so when I was talking about asking you the question over there, it's kind of like the opposite of that in this sense, and it's kind of like when I said, sorry,
You're fine.
when I was saying that X is the connected set, but a component, I mean, if X is disconnected, then but it might have a component that is connected, right?
Yes, it's very possible.
You're saying that if X is disconnected, then all of its components are just around one point itself, and that makes it totally disconnected.
Yes,
So
that's
there's
our
no
definition
connection
of
between
totally
any-
disconnected.
anything.
No two points are in the same component. Every point is its own component.
Does that make the component around the point still connected?
The point is the component, well, the second thing here. That's the biggest connected set you can find, a single point.
Does that make it disconnected? Or can it still be connected?
The set containing a single point is connected.
It's connected to
Okay.
itself, yeah.
You can't find two open sets containing that split that point into two sets. Yeah. Okay. So a set is totally disconnected, provided that the components of it are all just one element subsets. So let's consider the lower limit topology on R. What is the lower limit topology on R? It's the one whose basis elements look like this. Oh, we already talked about this one.
Yeah.
Yeah, reminder. So I'm saying, let's just make it make sense, kind of a big giveaway that this example comes right after this definition. Yes, this one is totally disconnected. This set is totally disconnected. What do we mean by that? We mean that any non-singleton set, singleton meaning it only contains one element, any non-singleton set you pick in here, I can split into two open sets.
Yeah.
So pick any set in there you want. Give me any subset of the real
Like,
numbers.
you get a single.
1 to 2.
1 to 2, I don't know if you meant to include or not include any of those.
Include one.
Let's not include 1 and include 2. How's that? There is some random subset of R. And I'm saying this thing is not connected. Right? Let's draw on the number line to make it more obvious that's not connected. We've got 1 to 2, it looks like that, right? I can divide that thing into two open sets real easy. I can divide it into this open set with this open set. You see that? Now every point in here is in one and only one of these two sets. Notice how that's not the same thing on the standard topology. If this were the standard topology on R,
But I
now that's a different question.
thought they had to have one element. I'm confused.
I'm saying that this set is disconnected, not connected. The connected sets are single
Yeah,
element
but you're
sets.
saying this whole thing is totally disconnected.
Totally disconnected. Meaning
There
that
doesn't have
the
to be one element.
meaning that the biggest connected sets that you can find only have one element. Because if you give me any non-empty subset,
But you just, the biggest connected element you can find can be split into two, right?
this is, I'm saying pick something that's disconnected. It wasn't connected. Anything you pick is going to be disconnected unless you happen to pick a one element set.
Okay.
So this, the set containing 3, okay, yeah, that's connected. This thing over here, not connected. This is disconnected. Any subset of R you give me that has more than one element in it, I can find two intervals that look like this that contain all the elements of your set and are disjoint.
Right.
And it's real easy because you just bump them up right against each other like that and stretch them out as far as you need to contain your whole set. Okay. So there's an example. And then finally, components are preserved by homeomorphisms. So let f from x to y be a homeomorphism, so that means x is a topological space and y is a topological space. If c is a component of x, then f of c is a component of y. Understand what we're proving?
Yeah.
Okay, so let's prove it. Since c is connected in x, then f of c is connected in y.
Yeah.
That's what we did back there. Homeomorphisms preserve connectedness. We already talked about that. So, since c is connected in x and f of c is connected in y, so that means that there must exist some component d containing that connected set. So I know f of c is connected in y, so f of c is in some component, call it d. D is y's component containing f of c. Turns out they're going to be equal, but so far we just know that there has to be some component containing that connected set, right? So there exists some d in y such that f of c is a subset of d, and d is a component of y.
Okay.
Good so far? Okay. Since d is connected in y, then its pre-image is connected in x.
Yeah.
So, since c is a subset of the pre-image of d, since I know that f of c is a subset of d, then c is a subset of the pre-image of d, and since c is a component, then c is equal to f of d.
I'm a little confused on how you got that. Yeah.
C is in this connected set.
Yes.
C is everything that's related under the is in the same component relation.
Is in the same connected set?
Is in the same connected set, thank you. Is in the same connected set. Everything in this set is in the same connected set as everything in this set, right?
Yeah.
And they have an element of C. So this is going to, I probably should have specified, C is a subset of this thing, and since these two have a point in common, and since they're both connected, then this thing also has to be a subset of that, therefore they're equal. That probably would have been a better way to do it.
Yeah, I see that now.
Okay, so just because connected sets have a point in common, and C's all the ones that have a point in common with some particular point. Doesn't matter which one you pick, because it's the equivalence relation. Okay, so then we got C is equal to the pre-image of D, and therefore f of C is equal to D. Because don't forget, this is homeomorphism. 1 to 1, not 2.
Yeah.
And that's it. Nice big section. Next section won't be as big.
So that's all on connectedness?
That's just getting started. The whole chapter is on connected. This was section 1 in the chapter. We've got 4 more sections to go.
Oh, wow.
Yeah, we got connectedness.
Metric spaces.
I don't know if we'll do 6.3. It's a fun one. It's proving the intermediate value theorem. Because now you have enough to prove the intermediate value theorem once you have a connected topological space.
Okay, done.
Yeah, maybe we will do it.
We should, because that doesn't make any sense to me.
Yeah, the intermediate value theorem gives you quite a bit. That's the main thing that we'll be using tomorrow. I assume you don't have any questions about stuff, so I can turn off the camera.